Welcome to the Hydro-metallurgical processes simplification by simulation using METSIM course. My name is Shingrai Dube and I'll be a tour guide through this journey as we try to simplify hydrometallurgical processes by making use of simulation. So this will be our general map of this initial module. We're going to have about 6 modules. This is the first module, where we are just basically introducing the theory involved in our course so that we build a strong foundation for the practicals that will follow. So this will be basically the introduction. Then we move on to the mineral processing aspects that we'll be dealing with. In this particular instance, it will be a hydrometallurgical course. Then we move on to how we actually link the hydrometallurgical processes with simulation. Then I'll briefly introduce the software which we'll be using, which is called METSIM. So generally, hydrometallurgy started it dates back to even the 7th century, where an Arab called Jaber discovered aqua regia. Aqua regia is actually still being used. Imagine, it was discovered around the 7th or 8th century. Now, hydrometallurgical processes are a small portion of the general mineral processing. We have other ways to actually extract our valuable minerals, your pyrometallurgy and other processes that are continuously being discovered. So this is a general map of usually the unit processes that happen in the hydrometallurgical industry, whereby we start by mining, then we go on to size reduction. Once that is done, we go on to concentration. Then we go into the hydrometallurgical processes themselves. Then we move on to purification. Then whatever remains goes to the tailings. So as I said initially, the initial process is the actual mining itself, whereby our ores are mined and then they're sent to the comminution circuit. In the comminution circuit, it's basically we are just reducing the size, as there will be big boulders that need to be reduced so as to actually improve the efficiency of our systems. Now and again, as our processes will not be 100% foolproof, usually we tend to use screening to actually screen the bigger chunks so that they are returned back to the comminution circuit. Once this is done, we now need to concentrate our material which we would have recovered from the comminution circuit, so that we now deal with smaller quantities. Again, the major purpose is actually to make sure that our processes are efficient as possible, and then we do not waste much energy in the other processes that will follow. So what exactly is hydrometallurgy? It is basically the extraction of metals from ores by dissolving the metals as one of its salts, and then we recover this precious metal from the solution. That's basically what hydrometallurgy is. So in general, the working temperatures in the environment are relatively cool. Usually room temperatures are actually utilized for hydrometallurgical processes, as opposed to the pyrometallurgical sector, whereby higher temperatures are used to actually extract the valuable mineral. So there are basically 3 classes of hydrometallurgy. The first one being leaching, and the second one being solution concentration, and then purification. Then we have our metal or metal compound recovery. So we'll kickstart with the leaching process, which is perhaps the most important stage in the hydrometallurgical cycle, as without it we will not be able to go forward with the actual extraction of the minerals. So it is basically a process of removing metals from materials that contain the metal itself, the valuable metal, from aqueous solutions. So of importance is to note that in leaching, mainly it's aqueous solutions that are actually what used. So there are many factors that actually govern the leaching processes. For example, your reagent concentration, your temperatures, your mixing velocity, sorry, your solid surface areas, your pressure. So I will just basically try to visit a few examples of leaching processes. First off is the in situ leaching, which is a process of actually recovering metals. Usually, this process is used to recover uranium from deep deposits, whereby boles are actually drilled deep down into the ore body. Then another pump actually pumps this solution, which would have now dissolved the wanted mineral itself, back to a processing plant, which then strips off this this solution, which I'll explain further later on, is this is a common process throughout all the other leaching processes. The other process is heap leaching, whereby we crush materials from the run of mine. We crush the run of mine into small chunks, then we heap it. Then we sprinkle a solution of our leaching agent, which then dissolves the wanted mineral, forming what we call a pregnant solution. Once this is done, the pregnant solution is then stripped off. As I said, I'll explain again this process later. Then we move on to vat leaching, whereby we have vats which contain the solution, the leaching solution. We put our ore inside these vats, and then the solution dissolves again the wanted mineral, and then we strip off the solution of the wanted mineral, and then we move on to the next stages, which I'll explain later on again. Then we have tank leaching. In tank leaching, it's the same as vat leaching, but the only difference now is that there will be motion involved. So as you know, once you start stirring things, for example, in when you're making tea, you actually stir so that the sugar dissolves faster. So it's the very same concept with our tank leaching. So you put your minerals inside, then they actually dissolve into the solution by making use of stirring. Then you have your autoclave leaching. Under the autoclave leaching, it's the basic same concept, but the only difference now is we make use of higher pressures. So from if we recall from A level, from Henry's law, that gases diffuse faster into liquids under higher pressures. So we use this same concept under autoclave leaching. So once the pressure is increased, our rate of reaction is actually what? Also increased. So once we actually have our leaching solution, the pregnant solution, it then moves on to the concentration and purification processes. So, for example, in the copper industry, they make use of electrolysis, whereby the solution undergoes an electrolysis cell, whereby it's then the ions move to the cathodes and the anodes, and then we have our pure metal being actually retrieved from that process itself. Another example is in the gold industry, whereby you have your activated carbon and then that activated carbon is introduced to a solution. It then grabs the wanted material, which is our gold, into the activated carbon. Then this activated carbon is then transferred to a boiler, where another leaching solution is then used to strip off that the wanted gold from the activated carbon. Then it goes on to the purification processes, which I won't discuss as they are under pyrometallurgy. But yeah, that's basically the process of actually concentrating in purification in hydrometallurgy. So then now, the important question now is what exactly is the link between hydrometallurgy and simulation? So in simulation, it is actually a process of basically simulating a system or a process in real world time, whereby you have a process you know, then you're trying to imitate it, so as to better understand it and to make changes before actually doing the actual process. So you find that industrial firms that have not yet integrated this technology into their production, uh, these firms actually miss out on a chance to research their systems before actually implementing, as I was saying earlier on. So simulators can be actually useful, particularly in the light of the significant expenses associated with commissioning new production facilities and processes, especially considering that the once you've built a plant and it undergoes failure, you can imagine sometimes commissioning plants can cost up to billions of dollars, only to realize that you made a mistake in certain processes, which you can actually avoid by use of simulations. So, what are some of the advantages of simulation? You actually get to identify manufacturing constraints. You get to see your bottlenecks, your all those problems, and you get to see potential possibilities to actually increase your throughput. When you put your simulation under vigorous exercises, you actually get to experiment more. You do everything you want without actually incurring extra costs that come by actually having to build the actual plant itself. So it actually outlines a potential cost saving measures by not in being involved in direct or indirect labor. You get to get people to actually build the processes and all those expenses. These are actually averted by making use of simulation. You get to also investigate how to anticipate the performance of value streams or production facilities. This is self-explanatory. It also actually gets you to improve your process quality by simulating real world procedures without building the plant itself. So, in the mineral processing industry now, the use of steady state simulation approach is now acknowledged to be a real aid for the process engineer in the design and optimization of mineral processing facilities. There are several hundred copies of simulation software that are used in the mining and mineral processing sectors, but you get to see why I actually chose to actually venture into METSIM in itself. So the capabilities of a program vary in terms of the quantity and the quality of the mathematical models, as these simulators make use of mathematical models to actually model the processes, whereby one first investigates how a certain process moves from A to B, then they mimic it by making use of mathematical models. So these are constantly being refined as people and technology advances and all those things that are involved. So all the steps of the simulation-based strategy, including sampling data, data reconciliation, modeling, simulation algorithms, and cost calculations, should be improved. That's when we make use of these simulation tools. Now, the simulation program, which we shall use in this course, is METSIM. So METSIM is all the basics. It is a general purpose process simulation system that is designed to equip the engineer in performing mass and energy balances of very complex systems. You'll see I will be getting into very complex systems that can be made easy, which was not possible with the use of pen and paper. You can imagine a process that will have, let's say, for example, you have a primary crusher, a secondary crusher, a tertiary crusher, then you have a combination circuit whereby you have maybe 3-4 ball mills in one circuit, then you have many cyclones and all those and all those. I'm just concentrating on the combination side of things. Now imagine, let's say it's a carbon and leach plant. You have many tanks also on that side. Now imagine having to do mass balances or energy balances of such a system using pen and paper, and you have to present uh, those figures in a matter of a short period of time. That will prove to be a very, very, very huge challenge. But then with METSIM, this is made very easy. You can easily input all your data, especially if you actually know the process itself you want to use. Uh, Besides that, it actually recommends, let's say, for example, you want to commission a ball mill, but you actually don't know the size. So you can give METSIM the option to input all the other data and then put your ball mill in the forefront of it. So you input your actual flow rates, your input, your outputs, your electrical supply, and everything, and it actually sizes a recommended size of the ball mill. This is one of the advantages of actually using METSIM in the hydrometallurgical sector. Now, the other reason I actually chose METSIM is it actually gives everything, every non-process in the mineral processing sector that has been discovered as of late. Uh, Chances are is there in METSIM. So the other factor that pushed me to actually use METSIM for this course is you get to not to shift softwares in between the project. You can imagine having to, let's say, for example, you want to simulate the crushing section, you have to use another software. Then for the milling section, you have to use another. For the leaching section, you have to use another. For your accounting, you have to use another software again. That will prove to be a challenge now, especially when you're now trying to complete the marriage between all those other projects. It will become hard. So you can see that it is a complete project simulation from your SEG ball milling to your flotation to your leaching to your cyanidation processes, your roasting, your acid and carbonate leaching, your base metal smelting, all types of leaching from your gold, your nickel, to your uranium, to your copper heap leaching. It's found in there. Besides that, it covers also the economic aspects so that you can actually get to have the economic side of things. As we now know, today engineers are not supposed to just give whether the process is actually feasible, but it should also make economic sense because at the end of the day, we are in it to make money. So if it doesn't have the economic aspects now, uh, it's rather a useless point. So that's that for the introduction. In the next module, we'll then start on the practical applications of actually using METSIM. We'll get into the general know-how of how to navigate METSIM, its capabilities, and also I'll introduce a bit on the language that METSIM uses, which is called APL. So I look forward to another great session with you. I hope you enjoyed. I hope this proved to be a good foundation for our course. With this, I thank you.